Okay, good morning. So, I am teaching now, you can stay if you want, or are you attending the lectures? You are attending the lectures. Okay, perfect. You are students of offshore. Yeah, sorry if I didn't recognize you. I'm sorry for that.
Which course we want to choose, okay. So that's why. Sorry for this. I think it's 4th or 5th class that we are here. So sorry.
Yeah, no problem. So now you are planning for the future to attend this course. Okay, this is perfect. And you can find the recordings, the videos of the previous lectures if you want, and that's it. Okay, are you attending also the lab, the laboratory? No, I don't think so. Okay, good. And you know that there are lectures also on Friday for this course because I am teaching just 3/4 of the hours, and the other 12 hours are taught by my colleagues Renacella on Friday. So you have 4 hours on Wednesday for me and 4 hours on Friday by my colleague. Of course, we are not expecting that you attend everything. Just wanted to inform you. Okay, very good, perfect. Okay, so basically, I want to start again from this slide because I think that now we have refreshed our minds about probability. Okay, so you know what is a probability density, you know what is cumulative probability or probability of not exceedance. And what you can see here is a picture of probability density distributions. Remember that the integral is 1. So if you take the integral of the density, it's 1, because of course the integral over the whole domain of the random variable is 1, because of course the probability of not exceedance of the largest possible value is 1. So the probability of not exceedance is the integral of the density, and therefore that's the point where we are now. And we discussed how the probability density is changing with climate change. Of course, it depends on the location, it depends from many things. But this is just a few examples where you may have an increase in the mean, you may have an increase in mean and variance, or only variance. Usually we have changes, combined changes for all the statistics. So basically, after climate change, you get a different density distribution. And now, of course, the problem is how to estimate the new density, okay? Because, of course, if we look at the historical data, we have an opportunity to estimate the density, the current density, the current probabilities. But the question is, what the future climate will reserve to us. And then I showed you, I showed you just an example of an analysis that has been done in the United States. And you see also the source. This is just a very rough, a very coarse map of percentage changes in the heaviest 1% of all daily events. Okay, and you see my note in red there, because this is taken, I just want to remind you, from the American Society of Civil Engineering. It's a presentation of 10 years ago. It doesn't specify how computation was carried out, so how these changes were estimated. This is an important question that we will discuss. Okay, so when you see some prediction about climate change, the first question must be how these predictions were estimated. And depending on the methods, you can derive different indications, different information. But we will answer this question later on. Just wanted to remind you, this is a question mark that we are opening now. I want to show you a similar figure, but now with more details for Italy. This is a recent contribution by my colleagues from the Polytechnic of Torino. And D is duration here and Q is the quantile. I'm trying to explain to you. And first of all, they refer to different duration of rainfall. And in the upper part, A, B, and C, you see hourly rainfall. In the lower part, B, E, F, you see 24 hours, which is different from daily, because basically when you observe daily rainfall, each day you make an observation. When we say duration with the duration of 24 hours, it means that we slide a window over hourly observations and take the max in a given period for a duration of 24 hours. So the rainfall with duration of 24 hours may go from 3 p.m. of today to 3 p.m. of tomorrow. The daily rainfall for today is from midnight today to midnight tomorrow. It's different. So when you see hourly rainfall, daily rainfall, it's a bit different. You may say there is not much difference. It depends. There can be some difference between daily rainfall and 24-hour duration rainfall. Okay. And so let's look at the hourly rainfall. What you see is the percentage variation, a map over Italy, over 10 years. And basically for different quantiles. So in the left, you have the quantile 0.5, which is more or less the average. So it's the average of daily rainfall, the change in the average of daily rainfall. Remember, if you got some knowledge of probability distributions, you can understand that with the probability of 0.5, of not exceedance of 0.5, you get more or less the average. You can just try to simulate in Excel and see if this is true, okay? And so on the left, both upper part and bottom, you see duration, quantile 0.5. In the central figure, the quantile is 0.95, probability of not exceedance is 0.95. Remember, the quantile is the inverse of probability, okay? So the quantile is you fix a probability, and according to a probability distribution, you estimate the corresponding value, okay? And on the right, the quantile is for probability of not exceedance of 0.99, 99%. So what we can see, what we can say, if we look only at the three figures in the upper part of the picture. First, we can say that for increasing quantile, there is an increase in change. And this is quite reasonable. If you think about probabilities and you make a change in, for instance, in the mean and variance of a probability distribution, then you expect that if you look at the extremes, they change more with respect to the average. And it's interesting to see the percentage change over 10 years. When you see dark red, it means that it's about 15%. Can be more, but basically this is what you can see there. You also see dots. The dots indicate the statistical significance of the result. Now, let me briefly explain how the data were derived. And so I am answering to the question mark that I raised earlier. They were derived by analyzing observed data. Okay, so this is a possibility to estimate the impact of climate change. You look at observations and you estimate the change in the observations. When you do that, you estimate the change, but there is uncertainty. So if the uncertainty is large, it means that your estimate is not very significant, is not statistically very significant. And uncertainty is resumed by the dots. So the dots, if they are large, it means that there is high significance of the results, less uncertainty. When you see that the dots are very small, it means that yeah, you got a change, but it's not very significant, the estimation. There is a lot of uncertainty. And the question may be, okay, but if I analyze past data, how can I project into the future? Of course, you may do it in a very simple way. Remember, in engineering, we are not refusing simple solutions. In some of the cases, we look for simple solutions. Why? Because simple solutions mean reduced uncertainty. Think of an estimate that you make with a very complicated method. Maybe that it's more precise what you get, but with a lot of uncertainty. I mean, the representation that you get is closer to reality, but with a lot of uncertainty because the method is very complicated. Instead, a simple solution probably is not as close as reality as the complex one, but maybe with less uncertainty. And in engineering, remember, we have also the duty, and we are responsible for that, for looking for uncertainty, and therefore considering uncertainty. And therefore, we don't refuse simple solutions. In scientific research, is a different story. In scientific research, you need to get a correct answer, and sometimes you are allowed to investigate complex solutions because you want to get a representation that is closer to reality. But in engineering, you don't have to refuse, as I said, simple solutions. So what could be a simple solution to estimate the change expected, for instance, in rainfall in 2100, basing on these results? A simple solution may be, okay, these changes refer to an observation period that is from, I don't remember here, but I guess it's from 1960 to today. So it's about 60 years. And therefore, this means that during the last 60 years, what did we get as increasing temperature? 1 degree. Okay, perfect. So if for a 1 degree increase, I got these changes, I look to predictions for increasing temperature up to 2100. There is 1 more degree. Okay, perfect. So I replicate these changes. I extrapolate these changes in the future, depending on the increase of temperature. This looks very simple, but actually it's very reasonable. Why? Because we think that the increase in rainfall is caused by the increase in temperature, because there is more retention capacity of the atmosphere to retain water. Okay, so this is a possibility. And actually, there are scientific papers proving, testing this approach. So you relate the estimation of the change in rainfall to the change in temperature observed in the past, and you project it into the future. And of course, to get the prediction of temperature into the future, you need some temperature predictions, which can be derived by climate models. This is a possibility to get an estimate of expected change by 2100. So basically, 2100 means 70 years from now, and you see that you can derive an estimate. Usually, be careful when you get the result, you have to make sure that it's consistent. It's, it's corresponding to your intuition, and how can we check it? We may look at the literature, what are expected changes for rainfall up to 2100. And one important thing, we can look also at, at the changes that we had in the past, like here, their statistical significance, and you have to test. And to give you a rule of thumb, if you get an increase of rainfall from now to 2100 of 100%, so double rainfall, it's not reasonable. It's not really a reliable estimate. If you get an estimate of plus 30%, 50%, it would be fine. Let's look again at the maps in the upper part of the figure. You see there is a lot of variability over Italy. Actually, we know that in the Veneto region, there is an increase of rainfall that is larger than the other regions. And also here you can see in the Piemonte region on the northwest, okay, of Italy. We know that, but actually now my colleagues are struggling to find an explanation. For what reason? Even if you look, a first explanation could be only over the mountains, which is reasonable. And but on the other hand, so the question becomes why only in the mountains of Veneto and Piemonte, a little bit Lombardia, but not too much. And these are open questions. Let's look at the bottom figure, daily rainfall, same thing, same quantiles, and you see that the increase is lower than, and with a different geographical distribution, which it's a bit puzzling. We can explain why daily rainfall is changed less than hourly rainfall. What is the reason? The reason is that we know that there have been changes in the short duration rainfall more than in the longer durations. And in the longer durations, it's about half of the increase for the hourly durations. And this is a bit expected because we know that the storms that have increased in intensity are those that are like summer storms. They are typically very short. There are changes in the geographical distribution, but this contribution, which was published just, I think, 2 months ago, in my opinion, is outstanding. And I'm showing it everywhere I go to talk about climate change. I think this is the first comprehensive map over Italy of observed changes in precipitation, and sheds really a lot of light on what we can expect for the future. Okay, let's forget about this. And this is not available in your, it's not available in the slides. The slides are not available to you. It's available on my website. I downloaded it from there. But in any case, just learn that when you know the reference of a paper, and very often the author's subfiche, you can go to Google Scholar, and let me show here, Scholar, or ChatGPT, but I mean, you know, when you have a reference that is more solid, it's and you search for Claps, Mazzolio, and the other ones are, let me see, Ganora, Viglione, okay? Ganora, Viglione. Let's see. I think it is this one, Journal of Hydrology 2025. Let's see if it is open. I think yes. And here is the paper. And let me see if it is open. Yes, it's open. Ah, yeah, it could be open because I am connecting from inside the university network, but the same applies to you. I'm not sure it is open outside the university, but you can find it here. And you don't need this for preparing your exam. It's just an example. Okay, good. Let me go back here and let's close it. Perfect. And I go back to the slides. Okay, we still have the question mark here, how they were computed. We will continue this discussion. And second, we will continue this discussion now. Actually, I forgot this slide. IPCC projections of extreme events. We already discussed about IPCC, Intergovernmental Panel on Climate Change. They make several projections available. Projections and not prediction. Why? It's a scientific debate, a scientific decision to call them not prediction, but projection. Why? Because with prediction, there is an implication, an hidden implication that is something precise. And they wanted to emphasize that projections is a bit highlighting that it's subjected to uncertainty. Keep in mind that the prediction of future climate are affected by uncertainty, and there is no way up to now to estimate it in a reliable way. You can find some estimates of uncertainty, but if you look at how they were computed, there is something that is implies approximations. And so IPCC is providing these projections, and how they are computed by using climate models, which predict the increase in temperature. We already mentioned that, but also predict the increase in rainfall. And the big thing is precisely uncertainty. And you will make with the professor that will come tomorrow in the lab, those of you who are attending the lab will make a download of climate data from a repository containing the results from climate models. It's very easy actually to download these. I mean, very easy, let's say. It's not very easy, but it is possible for everybody with a limited effort. And you can download changes in precipitation, and he will download changes in wind speed, and you will see how to do that. So this is the second option. The previous option was analyze observations, and then I use the results to extrapolate into the future. Second option, I use directly climate models. And why not? I mean, one could say perfect. Yeah, perfect if the model is precise. But keep into account when you try with the climate model to reproduce the observations, they fail. And there is a huge debate like, yeah, but the models are good for making predictions, not for reproducing the past. Keep in mind that if you go in front of a court because you are charged and you say, yeah, the models were not good in reproducing the past, but they are considered for making prediction. Basically, you are saying, I am making prediction of a model that failed to reproduce what has been observed. You are in trouble. Okay? From a scientific point of view, it may be something that you can justify in some way. And remember that scientists don't bear a direct responsibility in most of the cases. But in technical applications, usually we require that models are tested. And they are tested by simulating what we have observed. Okay? If you test the model and fails in reproducing what we have observed, from a technical point of view, to use it for making predictions is absolutely unjustified, unless you take some corrections, but in any case, you have to explain it. So climate models, unfortunately, have a level of uncertainty so far, not for all the variables, but in particular for rainfall. With temperature, they are quite good. For rainfall, so and so. It depends on the location, it depends on the scale. So if you simulate long-term rainfall, they are more reliable than short-term rainfall. They are improving. So maybe that in 10 years from now, and with the use of artificial intelligence, supercomputers, maybe they will improve, and then maybe that also we change our practices. But so far, just be aware that this is done in several cases, more for scientific investigation, management, for managing risk. Usually they are not used. Okay, but for management, you know, if you have to manage a reservoir, you can try to compare, to evaluate the information they provide. But of course, it is at least useful to see what they say. So downloading the data and looking at what they predict is something useful, and may be useful to integrate the estimates. So for instance, you may extrapolate, you may use different methods for estimation, and then take the most conservative one. This could be a possibility, provided that your structure remains feasible, the project remains feasible. Okay, and now let's look at in more details at the impacts on civil engineering, and now we go into some specific, we become more specific. So climate change, first of all, increased temperature and more severe heat waves. So what is the impact on function, lower heating, and greater cooling requirements? Health, safety, and productivity of occupants, impacts on integrity, sizing of this acronym, what could be? Let me see if it has been defined earlier. I don't know what is this acronym, just one second. Okay, let's
Health and conditioning.
Sorry? Air conditioning. Thank you very much. Durability of building materials. Second, climate change effect, increases of heavy precipitation and flooding, interruptions due to the flooding of sites on the functioning, the impact on the functioning, basement and lower basements and lower parts of the buildings may be flooded. And on integrity, failure from excessive water, ice, and snow loads on roofs and other exposed structures, erosion and scouring of foundation for bridges, for instance, water and mold damage to flooded equipments and materials. Okay. Good. Sea level rise, hurricanes and storm surge, permanent flooding of low-lying areas, losses in property values. This is a big issue. And it's a kind of a complication. I tell you a story. You know that Florence is exposed to floods. Florence was flooded in 1966, and the situation of Florence today is basically unchanged. They enlarged a little bit the aprons of the bridges, which means that the river has more conveyance. But basically, the situation is more or less the same. Keep into account that when they increase the conveyance of the river, means the capacity of the river to bring water downstream, they got the complaints from Pisa, which is downstream. Because, of course, if you deliver more water downstream, you may save Florence from floods, but you may flood Pisa. This is the first complication. But anyway, Florence is exposed, and therefore a couple of, I think it was like 10 years ago, something like that, probably more than that, 15 years ago, they thought it would be a useful information to publish a map over the phone register, over the phone list, because in the past, when we only had fixed phones, there was published by the telephone companies, they published a list of the persons with the address that had a phone number that were registered to the service. This was quite used. It was a usual practice. And when you were looking for a person, you had the register, the book for each city, and you looked in alphabetical order, and you could find the phone number and the address. It is something that today, with the privacy, is no more there. Anyway, 15 years ago, they still had it, and they published in the first page, after the cover, a map of the areas that would be flooded in case of failure of the system of the levees of the Arno River. Actually, they had to take it back after 1 week because the owners of the houses that would be flooded, they made they got very angry and complained because of the value of the houses. So basically, if you say that an house could be flooded, what happens is that the value becomes half of the value that was before publication. So, there are societal implications when you talk about climate change and risks, related risks that are, and for earthquakes, some years ago, there was a minister of infrastructure who proposed to make a catalog of the buildings and listing those buildings and those houses that were protected against earthquakes. So they were protected against seismic events, and it didn't pass. And he thought of making it compulsory for selling the houses, compulsory to prove that the house was earthquake proof. And it didn't pass. Because for the same reason, there are societal implications that are really. So, permanent flooding of low-lying areas, losses in property values, we were discussing this, evacuation for storms, and on integrity damage from high winds, forces of moving water and wind, equipment contents and material damages from water and mold, drought and wildfires and water use limitation, losses for agriculture and landscaping, evacuation of fire-threatened areas, foundation instabilities from desiccations, fire damages to buildings, content and sites. Okay, now, question, we have this possible impact. So what is the core question? How do we adapt our, and this is the main question of this course, how do we adapt our design project activities? Okay, how do we elaborate design projects in order to take it into account? And basically, it's the whole life cycle of the product or system, planning, design, construction, operation, maintenance, and renovation or removal that should be revised in order to get a satisfactory performance in terms of design projects. And of course, this revision, when you elaborate new solutions, you have to take into account the magnitude. So we come back to the question, how climate will change into the future. So what kind of information should I use? Should I base on the historical data analysis, on climate models? And, it must be sustainable, because otherwise you don't do anything. And this is the reality in most of the cases. What is the reason why, for instance, against flooding, we always complain after a flood, but all what we do is to recover. But usually we don't move step forward, or in some of the cases, yes, but there is not really a widespread and coordinated action to mitigate the risks. And the reason is that sometimes the solutions are not sustainable before of socioeconomic implication. So like the example of Florence, and the solution may be not sustainable because of lack of resources. And this is particularly a problem in countries with a low gross domestic product. Of course, rich countries, you see that usually, like if you see the Netherlands, they got protected in a very efficient way. And then there is also the problem that it's not clear how to move forward. This is why we activated this master degree program, to make it clearer how to move forward. Okay, and so first of all, before we move forward, let me concentrate on the current situation. What is the current situation? What we do normally now in engineering, whatever is the design project that you're involved with, is that usually we base our estimate to estimate design variables or project variables, whatever we want to call them. We use historical data. We use our experience, which means historical data, typically. So in order to estimate, for instance, the load of the snow over a building, we use historical observations of snow cover. In order to estimate the wind forces, we use historical observations. And the results are then translated in simple rules, like we know what is the imposed load by snow by the Italian laws. And you studied it for sure in some of the courses. What is the extraordinary load that you have to take into account for snow? These estimates are based on some statistical analysis. For the Strait of Messina, we have reduced record of wind speed. And based on this reduced record, we make a statistical analysis and say the bridge must be protected against, designed against a max wind speed of 270 kilometers per hour, as we discussed last week. But there is an implicit assumption here. The implicit assumption is that the past is representative of the future. And in statistical terms, we say that the process is stationary. Stationary means that the model that we use to represent the reality is characterized by statistics, and these statistics remain unchanged into the future. This is the correct definition of stationarity. Note here it's not provided, so I provided it here. Okay. There is one thing that I said, and the definition, I'll come back to these slides, okay? There is one thing that I said. I said the model that we used has statistics. So there is an implication here that the model that we use is a statistical model. And remember, stationarity then refers to a statistical model that we use to simulate, represent reality. Stationarity is misused nowadays because people use it to characterize, to refer to nature, to the reality. No, nature is not stationary. Nature has only one trajectory, doesn't have statistics. It's the model that is, if it is a statistical model, then can be stationary. And stationarity, once again, means the statistics are unchanged. So average, variance, or standard deviation, same thing, and asymmetry, they are unchanged when sliding over time, when moving over time. And so it's no surprise that some people wrote a very popular paper, Stationarity is Dead, which means that if you use a statistical model to estimate future behaviors, you can assume, we have seen that the probability distribution after climate change changes. And they say stationarity is dead. The problem is that, first of all, here one could put there a lot of references because the paper was highly criticized. And what is the reason of criticism, basically? The reason is that if you say that current engineering practices are dead, you have to indicate what are the new ones. Otherwise, if you don't have a new one, to me, the old one remains valid. Because if it is the only alternative, then I have to use it. And then I may correct the results in some way. But so when you listen about stationarity, now you know what it means. It means that we use a statistical model for estimating a desired variable into the future, and we assume that the statistics of this model are unchanged over time. It is what is written here in a more correct way. Keep in mind that here you see that there is a difference between strict and weak stationarity. Let's forget about it, okay? One could say that stationarity is weak if only mean and variance are unchanged, and the other statistics can change. But let's forget about it, okay? It's not our interest, really. And also they refer here to stochastic process. Stochastic is, let me say, in a very simple manner, not fully correct, but stochastic is a synonym of statistic. Okay, so if I say a stochastic model or a stochastic process is a synonym for model. And when you say a stochastic process, it means a statistical process. Okay, it's actually there is a bit of differences, but let's just to clarify, and therefore all the statistics are supposed not to change, and but we don't have alternatives. Just keep in mind that current engineering practice, with few exceptions, there are some non-stationary models, but with few exceptions, very frequently, when you estimated last year the Gamble distribution, I don't remember what you estimated for the future for calculating the extreme values, it's based on stationarity. You take past data, and unless you don't use a non-stationary model, which I'm sure you didn't take into account, we will take into account non-stationary models in the second course of this spring of this curriculum, actions on structure and infrastructure. Okay, now you know what is stationarity, and here you see what they write. While it is important to learn from the past, such as learning from failures, the environment for engineering projects and systems never has been stationary. So actually, climate change is not a new thing. It is new in its patterns. But if you look at the past, there have been other changes. So I mean, this assumption of stationarity, these methods for engineering design have been tested in the past. And you may ask, but if they are not precise, if stationarity has never been valid, so what? But remember that we have safety factors. And indeed, engineers always used safety factors for this reason, because we know that whatever method we use for calculating forcings, there is uncertainty, and the safety factor allows us to take uncertainty into account. So my reply sometimes when people really struggle to say, what can we do with the current climate change because it's larger than we have ever experienced. My reply sometimes is, what's the problem? Just increase the safety factor. So if you use 1.5 now, use 1.7. You increase it to 10%, 20%, based on your, and this is reasonable. I mean, also in front of a curve, it's fine. Okay. And remember, we have to find solutions, and these solutions sometimes can be very simple. It's not really needed that you take everything into account if you don't have the means to take everything into account. Okay. So it is indeed this a big dilemma, and I very much agree with this slide. So planning and design of new infrastructure should account for the climate of the future. Designs and plans, as well as institutions, regulation, and standards will need to be updated. But there is great uncertainty about potential future climate and weather extremes. So this is the dilemma. So we need to update, but there is this question open. The next slides introduce two potential solutions to deal with the problem. But remember, you will see they still leave open the question, what climate can we expect in the future? But indeed, what they present now is very interesting. First of all, low regret strategies. Low regret means that, in a way, you always have alternatives in engineering. Even with the same cost, sometimes you have several alternatives. Choosing the low regret solution means that in case the choice you made turns out to be wrong, you have the lower regret. And this is a possibility, and it became a puzzle in the past 20 years, low regret solutions. But indeed, it's a very good suggestion. And adaptive strategies. This is the other suggestion. So, organize your project, your building, your infrastructure in a way that can be adapted. So now you make an investment, make sure that the investment is not thrown away if the climate in the future is not what you are expecting. How to make sure? First of all, by minimizing the part of the investment that you throw away, low regret. And think of a structure that can be adapted. And this is very often possible. And we'll see it with more details in the next slides. And there are several examples of low regret solutions that have been adopted. A possibility could be that usually when do you need a new project? When there is a problem. So there is a climate problem, which turns into an engineering problem, like or you have an environmental problem like an earthquake, and you need to design new buildings to organize a reconstruction. And of course, you have to make a prediction in this case, the earthquake is not affected by climate change, but still there is uncertainty. So what is the magnitude of the earthquake I should protect against? So a possibility is that you refer to what happened, you have a problem, you solve it with the current level of information. And in this way, you minimize the cost of the intervention because you don't get protected on something larger, which requires more costs, can be not sustainable. So basically, the idea is let's solve the current problem. In this way, as I said, I minimize the costs. People are likely to accept it because they were flooded, so they don't want to be flooded again. But in devising the solution, you make it adaptive. So in case it turns out that it's insufficient, you can gain another investment to update the solution. And this is in many cases possible. Okay? Not always, but in many cases, yes. So, for example, how can we move forward along this strategy? There is a method that is called observational method. And it has been introduced by Terzaghi, so it's not a new method. Okay, Terzaghi and Peck. So it's a geotechnical engineering technique, and it's also called learn as you go. And so you basically take into account uncertainty and you make a plan for adaptation. And based on new knowledge that you derive while constructing the infrastructure or after that, during the operational life. How can we move forward according to this? Okay, this is a slide that is very interesting, but it's not good for teaching, okay? So I just leave it to you just 1 second to say, read it. But let me move to the next one because it makes a synthesis. So basically, during the design, you estimate the most probable environmental conditions, like you do in your current practice, okay? But on the other hand, you incorporate considerations on the uncertainty of your estimate, like, okay, the future climate may be 10% more rainfall, 20% more rainfall. And then you identify the system alterations that you need to cope with changes. Okay, so basically, in doing the project, you move forward as usual, but you also make a plan for adaptation and identify also the worst case changes. So, for instance, prediction of climate models could be useful because you don't use them for the design. You use them for identifying possible situations, possible scenarios. So basically, it's not implying an increase of the cost at the current time, or there might be, because if you make a plan for adaptation, it has a cost, but it's not really a huge, usually it's not really a huge increase of resources that is obtained. And in particular, let me go into more details. What we could do is, let me move to the next slide, and then I come back here. Basically, we select, look at this graph, I just want to explain you in detail, and this graph is taken from the American Society of Civil Engineering, and there are a couple of things that I don't understand, but I think that it is nice. Basically, there is the middle dashed line, that is the design that is most probable, so what I am expecting. This could be also a flat line, because this is referred to sea level, so it is a prediction of sea level. could be also flat line, like I assume that there are no more changes, or I take prediction given by extrapolation, by analyzing the historical observations, and basically I say, okay, let me just say that this is what I expect, and I estimate the project, I make my design basing on, this is a design curve to cope with the current situation. You see that the continuous line is flat because I make the design to cope with the current situation. But the design, I incorporated a strategy. I mean, I have clear strategy, what to do, how to adapt the structure if it becomes insufficient, okay? But let me design it, the design curve is flat for the current situation. At the same time, I identify two limits, an upper limit and a lower limit, such that if the current design passes these limits, I need to, the structure becomes no more able to cope with the sea level rise, okay? And therefore, in this case, for instance, you see this is the current design, I keep it, but then it may happen that after 10 years, in this case 15 years, I cross the boundary. It means that the structure is not coping with the environmental condition anymore, okay? And then I need to update the design modification. Up to a certain level, I mean, the level to which you update, so the amount of this vertical segment, the length of this vertical segment, it's up to you, but you have to get into the range of the operational condition of what can be sustained. And therefore, and then you adapt and you go straight, and then you get to a situation where you may, for some reason, decide to update it. And then you get into the future. What I don't understand here is that they correctly say that there is the distance between the two curves, it's uncertainty in sea level rise. What I don't understand is basically is why it is decreasing going into the future. And usually uncertainty of a prediction, when you go into the future, should become larger. Okay? And also, I don't understand why epistemic uncertainty means uncertainty that derives from a model that is not good. So the model is erroneous. Aleatory uncertainty is something that you cannot eliminate. You can also take a perfect model, but there is something that remains there. I don't understand why at the end of the story in 2100, they only keep aleatory uncertainty. So it is not explained. There might be a reason, for sure there is a reason, but or an assumption behind that. But so basically, I get a best estimate, I get my uncertainty limits, and with uncertainty, I mean not really uncertainty in the future climate, but it's a range of operation of the infrastructure, okay? Let me go back to the previous slide. So develop a monitoring plan. This is, of course, needed to detect changes in environmental condition and system performance. Establish an action plan. Perfect. Set decision points for implementing system alteration and monitor environmental condition and the system performances. Then you implement your action plan. This is a possibility. This is an example, and this is a bridge that they built in San Diego that can be elevated if the sea level raises. And here it's explained how they do that. I mean, there is it's very simple. They just raise the upper part and they put an additional you see here, there is no reference to these numbers. One should look for the original document, but very simple example of a bridge that was designed with the possibility of raising it, okay? And this means that in particular, they crossed, let me go to the graph here. And let me just see, okay, lower bound, okay, upper bound. Okay, this graph doesn't apply to the example of the bridge because basically this is the design line, but the bridge is raised when you cross, when the sea level increases, not when it decreases. So this should be the indication of upper and lower bound should be switched. So basically, the concept is very simple. You just identify design variables, you design the structure, you identify the limit of satisfactory performances. So you identify a range in sea level that is to cope with the current design. You monitor the sea level. When the sea level goes out of the range, you adjust your structure. Okay, and actually I would have, I want to say you again, if I had to draw this figure, it would be different, but I just wanted to give you this example, which you can adapt to the cases that you have to deal with. Okay, I think it's, yeah. Let's look at the summary, and then we go into more details of the question, what the future climate will be. So climate is changing, but there is significant uncertainty regarding the magnitude of the change over the design life of the systems and the elements of our built environment. It will be difficult to reliably estimate the change that will occur over several decades, long after the infrastructure is built. Engineering design plans and institution and regulation will need to be adaptable for a range of future conditions, condition of climate, weather and extreme events, as well as changing demands for infrastructure. So now what we have to learn is how to estimate the future climate, and the professors that will teach to you how to make the design will tell you how the design can be made adaptable. Good. So recommendations. Engineers should engage in cooperative research involving climate, weather, life, and social scientists to gain an adequate probabilistic understanding of the magnitude and consequences of future extremes. But there is no quantitative estimation here. Practicing engineers, project stakeholders, policymakers, and decision makers should be informed about uncertainties in projecting future climate and weather extremes. And this is a bit of a gap today in our scientific approach, because it's not clear what is the uncertainty associated to estimation of climate change. Engineers should use low-regret adaptive strategies, such as the observational method, to make projects resilient to future climate and weather extremes. Critical infrastructure that is most threatened by changing climate should be identified, and decision makers and the public be informed of these assessments. Okay, and then there are some references. And you see that there is a paper by Ralph Peck about the observational methods. It's applied in geotechnical engineering, soil mechanics. If you are interested, I think it should be public by now. Okay, and my conclusions. How forcings in the presence of climate change should be estimated. Still, we didn't say that. It's an open problem. It's an open problem. So at the international level, And we need to refer to international experiences and standards, not because abroad they are better in doing engineering, but just because we need to share experiences. This is the value of the international cooperation, international approach, to share experiences. What I try to do in everything I am committed to work and look at what the others did. We need to be critical to elaborate our opinion and make sure that we make checks. So what if? What if this estimate is wrong? And learn how to browse and interpret the web, because today international cooperation is possible, is very easy. But of course, we need to use communication means in a very good way. And I don't repeat what I said about artificial intelligence. It's very useful, but by definition, it's wrong. So also yesterday, I looked for ChatGPT, and because I am traveling to China next week, and therefore I had a doubt, like, should I take the visa? And then I asked ChatGPT, and ChatGPT said, yes, you have to take the visa. And then I went to the embassy, and the embassy said, no, there is an exception until 31st of December. So, ChatGPT gave me the wrong answer. It was not really wrong, but he didn't admit that there was an exception. And actually, I was a bit puzzled because I asked the professor that is coming tomorrow, he's from China, from Wuhan. And I asked him, and he said, no, you don't need the visa. So, but I wanted to double check. So I went to ChatGPT, and then I told him, I said, okay, you are more reliable than ChatGPT. And also yesterday, I found, I wanted to find another information, scientific. Fortunately, it gives the references. So I went to check, and it was fine. And it gave a very useful information, because I went to the paper, and the paper indeed confirmed the interpretation. Another thing that I did just yesterday, this was amazing. I asked it to translate a letter in Italian. It's amazing. It is very good. I mean, just minor things I had to change, and I am native Italian, so it is really impressive. And look at scientific reference and make a difference between a peer-reviewed paper and not reviewed sources. ChatGPT usually doesn't make a difference, and it just looks over ChatGPT or artificial intelligence. They look over the web. This is an advantage from one point of view, because it gives to you a more broad synthesis, a broader synthesis. But on the other hand, we have to take into account that there is a difference between peer-reviewed publications and sources that are not reviewed. And remember that climate change is a controversial topic, and there are biases in what it is published. So if you use artificial intelligence, just double check the references and try to learn what are the references that are biased, which is, I mean, bias is not a problem, provided you take it into account. It's like with models. And if you get an estimate that is biased, it's not really a problem. If you know that it's biased, then you take the bias into account. In fact, there are a lot of procedures in statistics for bias correction, because bias correction is perfect. I mean, you have a model that is good, but still biased. You correct the bias. And okay, and that's it. Perfect. Now I would like to move to a more technical part, trying to move into something that is more related to our mission, to our task, estimate design variables in the presence of climate change. And any question? Okay. Before I move to the more technical part, I just wanted to close with a consideration. So I think we can close this. Okay, and I think we can close also this. Very good. So this is the list of the links. I am skipping a couple of lectures, which I will refer later to. And I pass to this one, risk-based adaptation design. And but before I get into it, let me see. I think there is a PowerPoint or not. No, there is no PowerPoint. Okay, I have to take into account it because before I move to this, let me just make a consideration. Let me see if okay, the blackboard is there. Good. And let me pin the blackboard. Okay, good. So one thing that we learned so far is that we can start the climate change by using explanations and changes in probability distributions. So let me just write down an example of a probability distribution, density. Okay, so this is our case X. This is X. And let me write down a probability distribution here. So let's suppose that this is 0, the variable is positive. Several variables in each variable, but not all of them. And remember that sometimes we start anomalies, climate change, sometimes we start anomalies. So the current situation is 0, and you look at the future, so you may have positive anomalies, which means that what is the temperature is decreasing, but you may have also negative anomalies. If you remember how the graph of the future temperature is in terms of anomalies. But let me make reference to the and start at 0, and it becomes, and it is like this, okay? And then we have a future distribution to estimate. I just want to draw your attention on something that is very important for us, which I already mentioned last week, and there's something very important is the tail of the distribution. So this is the tail. This is the tail. Actually, this is the right tail. Okay. And this is the left tail. And in particular, here the left tail goes to 0, so it's limited, while the right tail is extended on the right. So why the tail is important? The tail is important because it describes the probability of extremes. And usually when we make the design, when we make the design against extremes, not against the mean. For instance, if I have a million of 100 years extreme. So the tail is extremely important because it describes the probability of the extreme. And what are the most important features of the tail for us? The length of the tail. So we say that the distribution is long tail when the tail is long. And another important thing is the area of the tail. Remember, the area is representing the probability mass. So the tail may be long The tail may be longer, but close to zero, close to the horizontal axis. This is the probability. It means that even if the tail is long, if it is close to zero, there is a reduced mass of probability there.
This or this will be parallel.
Sorry?
And the tail is close to the axis. It will join or it will remain parallel.
It depends. It can be limited. So if the range of the random axes is limited, the tail may go to zero. But usually in engineering, we don't have an upper limit for design variables. Like think of an earthquake. When you suggest an upper limit, that's equivalent, and therefore you may say, I mean, the tail is very close to zero, but you can't suggest an upper limit. The same for wind speed, can you suggest an upper limit for wind speed? And this is also the subject of some philosophical discussion, because some people say nature has upper limits, but yeah, there is an upper limit. If you think of rainfall, you could intensity of rainfall. You could concentrate over a point all the water that is in the group and release it to this volume in 1 second. Or this is an upper limit. But my reply was, yeah, but if you release it in 1/10 of a second, so if time goes to zero, the intensity goes to infinity, there is no upper. I mean, but this is a discussion that is not relevant to engineering. From an engineering point of view, it does make a difference if you assume an upper limit or a lower limit. You can say intensity of an earthquake is a scale of 30. Because with a scale of 30, everything is not so you can take it as an upper limit. Because it doesn't make any difference. So what is an example of a tail that involves a long mass of probability? Something, for instance, like this, okay? Remember, if you add mass to the tail, you have to decrease the mass somewhere else. So I can't make like something like this, okay? I take the same probability distribution with a fatter tail. This is not possible, because if the integral of this one is 1, the integral of this one is not. So this is not possible. What I can have is something like this.
Is it an upper limit?
If the limit is infinity, you may, it is not an upper limit. You may limit like upper range, correct? Upper range. And then here the thing that you have to make sure is that the area below the curve is 1. And if it is extended to infinity, you have to compute the integral from 0 to infinity. So it's okay. And this is a fat tail. It could be also shorter. I mean, the tail may be fat, but shorter. So this is a terminology that is frequently mentioned. So a long tail distribution. The Gaussian distribution is short tail, even if in principle it goes to infinity, but most of it is defined as a short tail distribution. The long distribution is a long tail. And the fat tail distribution, there are some examples. I don't have good examples here. But what is really important is to highlight that the fat tail is concerning. The long tail is concerning, but still you have a very reduced probability of getting an extreme, a very huge extreme. If you have a fat tail, it is more concerning. So when I was studying climate change, you have to look at the tail, how it is modified. And you know, a fat tail, but also long tail distribution, but with a different probability, because the fat tail is higher probability. What does it imply? It implies that we made an unexpected experience. And remember, in engineering, the surprise factor is really what we are concerned of. It's a huge matter of concern. The surprise, like there is something that happens that is really unexpected. I am studying now with a PhD student, a rainfall event that occurred over Greece in 2023. You may remember it. It was in the Thessaly region. It was a huge flood. I think 13 people were killed. And basically, if you look at, we have daily observations from 2007 to up to 2023, so 16 years. And the highest value is something like 50 millimeters per day. What they got in 2023 was 450. There is no way with a statistical model to reproduce it. No way. Okay. It means that indeed there is something long-tailed, which we cannot estimate if we look at only 16 years of data. We need more data, or we need a different distribution. We need a different distribution. So just keep into account that this is an important feature for us. And it is something that we have to define. If we want to estimate climate change in defining the future probability distribution, we have to define it. Okay, now let me go here. And let's talk about this topic. One thing, let me make a when I talk about risk associated to, for instance, an extreme event like the risk associated to an earthquake, how would you define it? Do you have an idea, or did you already study how to define risk? So what would you say? What is risk associated to sea level rise or an earthquake, but an extreme event? So let's say like earthquake. What is, how do you define the risk associated to an earthquake? Who dares to try to give an answer?
Maybe it's related, of course, to probability. So we focus on a limit value. And if we will face this value, we are in front of a risk.
Okay, this is, I would say that this is not a definition, it's like an indication of the definition, but other ideas? Okay, if I write an equation like this, risk is given by the product of probability times vulnerability times exposure. Did you start it already? Yeah. In which course?
Agency, offshore agency, health and safety environment.
Okay, okay, okay. And what about you? Did you study it already?
Just previous lecture. So she told us about
Okay, just wanted to
Just state definition.
the definition. Okay. Very good. I have to make sure that we don't teach the same thing. Anyway, I want to focus precisely on the estimation of risk because this could be a criteria for making our decision. So let's study the adaptive features of an infrastructure or structure by focusing on the solution that gives the lower risk. And, you know, risk is not only related to probability, but if you studied it in offshore, I think it is something that you already know. Not only related to probability, because, for instance, an earthquake would be very likely in an area that is not populated. And you know, So it's not real. I mean, earthquake occurs, and that's it. And also, an area, it must be related then also to something related to people, to the value that are affected by the event. So if an earthquake occurs where in a city, there is a risk, there is a concern. Why? Because buildings are destroyed, or people may lose the life. But let's forget about the life of people for now, because it's a more complicated thing. Let's focus only on goods, assets. So there are buildings that you reconstruct them. So there is a damage, an economic damage. Okay. Or, okay, let's just focus on this example. And this is the value of the goods. And the value of the goods is the exposure. What we call exposure. Okay. But it's not all probable. And of course, you must have a probability of the event, because if the probability is zero, there are goods exposed, but there is no risk. You are not concerned. Okay. But it may be that these buildings are fully seismic proof. Okay. And therefore you are not concerned. There is no risk. Because, I mean, the earthquake occurs, there are buildings, but the buildings resist to the earthquake, so no problem. And therefore you need to introduce a third part, which we call vulnerability. And then we articulate the definition of probability, vulnerability, and exposure in a way that we combine that as a product. This is the risk equation. And this is a question that you will find frequently at the exam, something related to this equation. And also we will discuss additional factors that may be introduced here. But this is the definition of risk. So risk is the product of probability, vulnerability, and exposure that is accepted by the international literature. There are references here that I'll mention. Of course, the definition doesn't tell you how to estimate it. And also this definition that I provided so far, the product, doesn't really specify entirely how risk is defined, because what is the meaning? What is the meaning of risk then? What is the range? Probability, we know that varies from 0 and 1. And let's focus about probability of not exceedance. It's between 0 and 1. Okay. And yeah, for this equation, usually we express probability in terms of probability of cumulative probability. Okay? Probability of not exceedance. Because, of course, think of an earthquake, we are not interested in precisely in what is the probability of an earthquake with scale 5. We are interested in the probability that scale 5 is not exceeded. Okay, and therefore it's the probability of not exceedance. And so it's between 0 and 1. But about the other two, we didn't say anything. So how can we estimate them? And then what is the unit of risk? And because probability is dimensionless. But the other two, we still don't know. What is the unit, and therefore what is the meaning? Okay, because risk, how it's measured, what is the real meaning? So the definition is not complete. And I just want to dedicate a bit of time, and I'll make sure that Serena doesn't say the same things, to investigate and discuss how we estimate these three. And okay, so first of all, it's essential that we focus on probability. You know what is, okay? It's probability of not exceedance. And then we have to find a way, but I'm not replying today to this, to estimate the probability under the future climate of a given event. For today, let's refer to the current climate, okay? Current climate, current situation, current state of the system, and let's assume that we have a way to estimate it. And we know that it's between 0 and 1. If probability of an event is 0, we know that axiom of Kolmogorov, it means that the event is impossible, there is no risk, okay? But actually, let also me say that there can be multiple risks. And today, it's a topic of increasing attention because we realize that with the development of society, we are getting increasingly exposed to multiple risks. And then probability becomes more complicated. It can become a joint probability. We didn't discuss it. And what does it mean, joint probability? First of all, if you have two risks, like a risk of an earthquake and the risk of flooding, can they occur together? The first reply could be absolutely they are independent. If they occur together, it's just by chance. Actually, we realized recently that it's not true that they cannot occur together. Why? Because when the earthquake in the Emilia-Romagna region occurred in 2012, the levees of the river were damaged, and it was a fortune that the rivers were not full. But if the earthquake, instead of occurring, I think was May or something like that, occurred like in a season of high flow, who knows, you know? And also there was a problem in 2012 with the groundwater surging and originating some, I don't know how to call them in English, flooding of sand. Because I mean, with the compaction of the soil, there was an earthquake, the soil compacted and the groundwater was pushed up. And when it was pushed up, it mobilized the sand. And therefore, we got some geysers of water plus sand. There was a picture, I don't have it, which was amazing, of a car in the box, and they got a geyser of sand just beneath the car, and the car was pushed against the floor, completely destroyed. Only with water, you wouldn't get an effect like this, because of course, water is not as viscous as the sand. Sand really raised the car, and it was completely destroyed against the floor, the ceiling, sorry, against the ceiling of the box. And so, I mean, this is really something that is interesting. And how do you describe these compound events, they are called, or cascade of events? So an event that triggers other events. They are described, you can describe them with a joint probability distribution, which means that you don't study the probability of one event, but the joint probability that you toss a coin and get the head, and you roll a dice and get a 1. And you can estimate this probability. This is an example of two events that are completely independent. And if they are completely independent, you get just the joint probability by multiplying the two probabilities. So I toss the coin. What is the probability of getting a head? Is 0.5. I roll a dice. What is the probability of getting a 1? Is 1/6. So it means that the probability of getting a head and 1 is 1/12. Okay? But if the two events are not independent, then the probability is larger. So it's not, if I could find a relationship between the head and the 1, that the head implies the 1, then of course, if you get the probability of getting an head and a 1, that is larger. So there is a lot of research on these compound events through joint probabilities, which makes the problem really fascinating. And today is really a matter of interest. And for instance, I was contacted a couple of weeks ago by a person who said we have to urbanize an area, it's exposed to earthquakes, and the floods. So I want to know what is the risk, what is the associated risk. And in this case, one has to look if there is a relationship. So first you estimate the probability of flooding and then the probability of getting an earthquake, and then you have to investigate the relationship. And it's not easy because these compound events are very rare. You have few occurrences. So using only historical data is very often doesn't suffice. So it's an interesting, but now we focus on only one, okay? And because it's simpler, and the extension is not really conceptually different. It's not conceptually more complicated to compound events. It is more complicated to find the correct method because you have reduced information and it is, but let's focus on just one risk, okay? And then let's focus on the estimation of probability, vulnerability, and exposure after the break. So we meet at 2 sharp. Any question? Okay, good.